Okay, so this is our final lecture for Chemistry 729 on mass spectrometry. So this will cover our third lecture that was scheduled. And today we're going to talk about how we design experiments. And as you can imagine, we could probably spend 3 or 4 class periods just on this topic in and of itself. So what I'm going to talk to you about today is actually going to be quite brief, but we'll give you an idea of what you need to be thinking about when you sit down and try to design an experiment where you're going to use mass spectrometry as the tool for analysis. Okay, so the first thing that you need to know anytime you're getting ready to design an experiment is you need to know the instrument capabilities. That's very important. All of our instruments don't have the same capabilities. They have varying pros and cons, as you all remember. So they've got strengths, so they've got weaknesses, they've got limitations on mass, they've got all kinds of things that you need to take into account. So you always need to think about, is this experiment going to be more appropriate for MALDI? Or is the experiment going to be more appropriate for electrospray or APCI? And we've talked about those various ionization methods that we have at our disposal here at the University of Southern Mississippi. So as an example, if you were going to do a analysis of a synthetic polymer, not a biomolecule, you're probably going to want to focus on something like MALDI. MALDI has all of the right capabilities for that type of analysis. However, if you're thinking about looking at small molecules or small molecules being adducted to larger molecules, you may want to think about electrospray or APCI as your choice. So you always want to keep in mind the instrument capabilities. Okay, so let's look at an example of a real world type thing that you might be interested in and see how we can work our way through designing an experiment to detect what we're interested in. So let's suppose we have a mixture of fatty acids that are unsaturated, or excuse me, saturated. So we got, some mixture of them, so they differ by the number of methylene units. And these are fatty acids. Obviously, they're typically relatively low molecular weight, which might suggest that electrospray or APCI might be the way to go as opposed to MALDI. So we know that they're low molecular weight species. We have a variety of different molecules in there, so we might want to separate them using something like HPLC. So again, indicating that this might be the best way to do this is through electrospray ionization using the LXQ instrument that we have, because we can couple it directly to an HPLC system, right? So all of this seems to suggest that we might want to use our LXQ system or our electrospray. The problem that we have, however, right, is that they're not terribly polar. Yes, there's some polar functional groups, but they're not extremely polar, right? You've got this group here that can actually pick up a proton, for example, but it's actually not a strong Lewis base. So there might be some issues with getting this to ionize the way that we want. However, what we do know is that carboxylic acids are weak acids, and so if you think about a carboxylic acid, right, and I'm just going to represent the tail with R here, we know that these are in equilibrium in solution with their carboxylate. Right, at just about any pH, except extremely low pH, this equilibrium exists, and you might think that, well, look at that. We have our carboxylate, it's in the negatively charged state. Maybe we could just do negative ion detection, and in fact we can do that. So you could look at negatively charged ions in the mass spec and get their mass to charge ratio, because again, it doesn't matter what the charge is, positive or negative, it just has to have a charge. And so we can turn the instrument to where it looks for negative ions. And so a lot of people will actually do this. They'll run their HPLC, they'll run it into the electrospray system, and they'll look for negative ions, and they'll be able to detect the mixture of carboxylic acids they have. However, I will say this. and I'm not exactly sure why this is the case, but negative ion mass spectrometry is usually messy. Okay, so it has issues. It usually gives messy spectra. You see a lot of background noise when you're looking at negative ion spectra for the most part. And so that could create a problem for this. So how might we solve this particular problem? Well, as you can probably expect coming from me, we're going to use chemistry. So let's use some chemistry to fix that problem. Okay, so we know that negative ions are going to be messy. We really want to look at positive ions. However, the carboxylic acid is not positively charged. So what can we do? Well, we can put a charge on it. And one thing that you can use is something that it already has a formal positive charge on it. And one of the reagents that we developed for part of our Of course, the pyridine having 4 bonds to it is positively charged, right? And there's a counter ion, and in our case, it's bromide. Okay, so we make these pyridinium bromide salts that have a free amine on the end. It's got a couple of methylenes spacer. We won't go into how we make this, but we can take this now and react it with our carboxylic acid mixture. Okay, so again, I'm just going to represent the carboxylic acid mixture with R. And we can use a coupling agent, something like DCC. So you all remember that DCC will couple carboxylic acids and free amines to make amides. This is what you learned when you took your your sophomore level organic chemistry course. And so we're going to couple the nitrogen and the carboxyl group to make an amide. And when we do that, and I'm just going to put PY for pyridine, and I'm going to put a positive charge out here. Okay, so you end up with these pyridinium salts, and now your carboxylic acid has been converted into something that has a formal positive charge associated with it. So now you can take this mixture, you can run it through your LC column, your liquid chromatography column, and as your peaks come out of the column, you will then get mass spectra, whatever the peaks look like, right, for each peak that comes out, and you'll be able to see those masses. Now, of course, you have to take the mass of this and subtract it from the mass that you calculate here to get what your acyl group mass is, so that you can identify your starting carboxylic acid. But nonetheless, we can use chemistry, do a few reactions to actually do this type of work very, very easily, put that positive charge on there, and now we have a very sensitive technique. And what I will say is that when you put a positive charge on a molecule like this, you can get down to extremely low concentrations in solution and still be able to detect it, because all of the molecules are positively charged. Unlike over here, where we were depending on the equilibrium, right, depending on the pH, but the carboxylate itself, as the negative charge, would be a very small and minor contribution to the overall concentration in this equilibrium. So again, using chemistry is the way to go to look at this. Now we're going to look at a couple other examples here in just a moment, but give me a moment to erase and I'll restart. Okay, so let's look at another set of experiments that we can easily devise using mass spectrometry. And again, I'm going to focus largely on electrospray because I think it's the most versatile of the techniques for doing these types of experimental designs. But we can actually devise what are known as T-joint. Whoops, let's see if we can get my pen to work here. There we go. T-joint experiments that make use of what's called, as you might expect, a T-joint. So in mass spectrum, or well, actually in liquid chromatography, they make these joints called T-joints that look like a T, and you can screw in a variety of pieces of tubing. So you can have the T-joint that goes out, which would go to the mass spec. You can have this joint coming in. Let's say that's coming in from the HPLC, so the flow from the HPLC is going into that T-joint, going through to the mass spec. And then you can have this joint where you tie in some sort of reagent that is being pumped in by a syringe pump. And so as peaks are coming out of the HPLC, they're getting mixed in this T-joint with a reagent. Some chemistry is going on in line that then gets detected by mass spectrometry. So this type of experiment can be done for a variety of different purposes, but one of the things that you can do is you can actually use it to detect things that otherwise would be difficult to detect. So let's suppose we have a molecule that has some double bonds. Okay, so otherwise it's just a pure hydrocarbon. It's not polar. It's low molecular weight. It wouldn't be feasible really for MALDI for the most part. Electrospray ionization is not going to easily detect it because there's really no place for it to pick up a good charge. You might be able to do APCI, which is definitely a possibility. But again, there are reasons why you may or may not want to use APCI depending on what you're interested in. But what we do know is that double bonds like to form coordination complexes with things like silver or copper. And so you could react this with a solution of silver salt. Usually they use something like silver nitrate, or excuse me, silver triflate, and you can make, you can make these adducts where the double bond will coordinate with silver. And as you can imagine, that's now a charged species that you can detect by the mass spec. And so this works very, very well for this type of chemistry. You can also do other things with T-joints, again, where maybe you have two reagents coming together to form some type of reaction and you want to monitor that reaction over time. You could do that simply by varying the length of tubing between the T-joint and the mass spec, and that length of tubing would give you a different time for each experiment that you're doing. So you can actually do kinetics by these so-called T-joint experiments. You can do post-column modifications to get things that you can detect quite easily. So these types of T-joint experiments are actually very easy to do, very inexpensive. You can buy the T-joint from Upchurch for about $5–10 depending on where you order it from. Very, very affordable way to do these types of experiments. Another thing that you can do with T-joints or with other types of experiments is isotopic labeling. So you can do isotope label experiments very, very easily. And so let's look at an example. Let's suppose you have a protein, and I'll just indicate a protein by a random kind of shape, right? And you'll notice when a protein is folded, you have residues of the protein that are on the outside. So maybe like lysine residues that are going to be on the outside, and you have residues that are on the inside, right? And so you want to know, for example, how many of these residues are on the outside versus the inside. You could do this through an isotope labeling experiment because we know that NHs can readily be exchanged with deuterium when they come into contact with deuterium oxide. And so you'll then actually form the protein, and you can exchange off the hydrogens on the amine with deuterium. And what that does, obviously, is makes the protein heavier, and so you get a mass shift in the particular mass spec that you're looking at. So this is pretty easy to do. Now, of course, this experiment is overly simplified. You really wouldn't be able to tell the difference in just one residue being deuterated because the resolution's not good enough. But usually there are hundreds of different residues, right, that can undergo this so-called HD exchange experiment, and you can actually look at the changing mass distribution, and you can get an idea of how the molecule is, what part of the molecule is exposed to the water and what part of the molecule is actually embedded inside the fold. So you can do that with these so-called hydrogen deuterium exchange experiments. Very useful in the biochemistry community, and they quite frequently do it using this T-joint, where they'll have the protein coming in from some HPLC type column or whatever, you'll have the reagent, in this case just deuterium oxide coming in, and then you'll be able to detect the mass shifts as the HD experiment undergoes. There's other types of labeling experiments that you can readily do. You can do C13 labels. So you can do C13 labeling. Now that's not going to be as simple as using a T-joint experiment, but you can do C13 labeling where you have one molecule that is C13 labeled, one molecule where it's C12 labeled, and you can measure the ratios of those and get quantitative information. Biochemists do this quite a bit, either through C13 labeling or through nitrogen 15 labeling quite easily. So they will feed an organism, for example, carbon 13 labeled food, if you will, and nitrogen 15 labeled food. So you put this in like the media that you're growing your bacteria in, and you would be able to get what we call a standard bacterium that then you know the condition of. Maybe it's a healthy bacterium, right? Something that hasn't undergone genetic modification. And so you would look at the proteins from this that would be C13 and N15 labeled. It would give you a particular mass. And then you could do the experiments on the other bacteria, maybe where you're doing genetic modification or whatever the case may be, exposing them to some sort of disease state, for example. But you leave out the C13 and the N15, and it's just C12 and nitrogen 14. And so then you can look at the ratios of the proteins and use the labeled one as a standard by which you can make all of your comparisons. Okay, so there's a lot of pros and cons to this type of work. What I really want you to just take away from this is that if you're clever, right? So if you have a clever use of experimental design, you can determine a lot of things from mass spec. Remember in the first lecture I told you that in a mass spec all you really get is the mass to charge and intensity ratio of a series of peaks in the mass spectrum. But with clever design, using hydrogen deuterium exchange, using C13 or N15 labeling, T-joint experiments, those types of things, you can actually get a lot more information out of mass spectrometry than just these simple two variables. Because you're using your chemical common sense. And that's a very, very important thing to remember. Always think about your chemistry when you are designing these experiments. Think about the pros and cons of what you have. Think about the limitations of the instrument, and then be clever about how you design the experiment. You should be able to get a lot of information very, very easily. So that's all I really wanted to talk about today. I hope you enjoyed the video series on the mass spectrometry work. If you're really interested in going into more depth with this, I do offer a course on modern methods of mass spectrometry where we actually dive into these a little more than what I was able to do in these particular set of videos. So again, just kind of a high-level view, things that you can and can't do with the instruments that we have here. And if you have any questions, please don't hesitate to reach out. I'd be happy to help you design any experiments that you may be wanting to conduct.